Coming to the main topic of today's lecture, which is complex form of the Fourier series or complex Fourier series or exponential series. Um, it is called exponential series because it consists of the linear combination of the exponential function. So we will derive its form from the trigonometric Fourier series. So this is 7.6 section of the book Advanced Modern Engineering Mathematics by Young James. This book has already been uploaded on LMS. So let's see what is this complex form of the Fourier series. So you already know about the trigonometric Fourier series, which is given to you as this one. This one, trigonometric Fourier series. So I know that cos of x is equal to e to the power iota x plus e to the power minus iota x over 2, right? This one. And the sine x is equal to e to the power iota x minus e to the power minus x over 2 iota. So I can write cos k omega x equal to this one by using the definition. Here the angle is k omega x, so it is equal to this one, and I can replace sine k omega x by this identity. So when I substitute it equal to this, my Fourier series becomes f of x is equal to a naught over 2 plus summation a k cos of k omega x, which is equal to this one, and this is e iota k omega x plus e की power iota k omega x over 2 this one plus vk. So this is 1 over 2 iota. So I know that 1 over iota is equal to minus iota. So I can write, instead of writing it, I can write it minus iota plus iota. This. So it becomes minus iota e to the power iota k omega x plus iota to the power e minus iota k omega x over 2, this one. So what are the coefficients of, I can collect the coefficients of e to the power iota k omega x and this one. The coefficients of these are a naught plus 2 plus summation. ये बन गया मेरे पास e की पावर iota k omega x के coefficients आ गए मेरे पास a k over 2 और यहाँ से माइनस आयोटा v के ओवर 2 और दूसरे वाले e की पावर माइनस आयोटा k ओमेगा x के आगे कोएफिशिएंट्स a के ओवर 2 और यहाँ से प्लस आयोटा v के over 2. So I can take this coefficient equal to the new coefficient और ये आपके पास ये. So let's take it equal to C naught, this one equal to CK, and this one as CK conjugate. I can take it equal to CK conjugate because here, as you can see, that AK and BK both are real numbers. When I take the conjugate of CK, it becomes AK plus iota BK, which is equal to this. Or you can write it as C minus K. So my series become f of x is equal to c naught plus summation ck the power e to the power iota k omega x plus c minus k e की power minus k omega x. That is this one. This one. ये है एक और एक ये कोएफिशिएंट है और इसमें से अगर आई रिप्लेस माइनस के विथ के तो मेरे पास ये चीज बन जाती है और मैं इन तीनों को फिर इकट्ठा करके I can combine all of this then. दिस, जीरो को, नेगेटिव को और पॉजिटिव को, के को जब माइनस के से रिप्लेस कर दिया तो ये फिर मेरे पास ये चीज बन गई, यहाँ से के भी माइनस के बन जाएगा, इसकी रेंज। जीरो वाला अलग है, वन टू इन्फिनिटी ये वैल्यूज है, माइनस इन्फिनिटी टू माइनस वन ये है। तो इन सारों को आप ड्रॉ कर लें, इकट्ठा कर ले तो आपके पास ये सेम बन जाएगा, क्योंकि जब के को जीरो रखें तो ये आपके पास जीरो आ जाता है, तो ये सी नॉट ही एक कोफिशिएंट आएगा when k is equal to 0. तो आप you can combine this series. So this is my Fourier complex Fourier series or exponential Fourier series or complex form of the Fourier series or exponential form of the Fourier series. It is called exponential form because it contains the term exponential function. Okay. So I have derived this form from the trigonometric series. और इस केस में अगर आप इसको देखें, ये आपके पास रिलेशनशिप है जो हमने यूज किया था। Okay. So C naught is equal to 2 times A naught is equal to 2 times C naught. And if you have to find AK, then you have to add this CK and this equation. So by adding this into this one, I will get AK, which is equal to this one. And by subtracting this equation from this one, I will get VK, which is equal to this one. Up, you have to remember that these all coefficients A naught, B naught, and A naught, AK, and BK are real numbers, but these CK can be real, they can be pure imaginary, and they can be a complex number consisting of both real and imaginary part, as you can see. अगर यहाँ से मैं देखूं कि this BK is equal to 0, BK is equal to 0 means this CK is equal to CK conjugate. जब CK conjugate के इक्वल आ गया, then this AK is equal to 2 times CK. और अगर यहाँ से and if this AK is equal to 0, इसका मतलब है कि CK is equal to minus CK conjugate, that is the CK is pure imaginary, और यहाँ से जब आप substitute करेंगे you will get 2 iota CK. That is, you have two form, that is bk is 0 when the function is even, and ck is equal to ck conjugate, and you have ak is equal to 2 times ck. And if the function is odd, then a naught, these two are zeros, and ck conjugate is equal to minus ck, and bk is equal to 2 iota ck. अब आपको ये याद रखना है कि a naught, ak और bk ये तीनों trigonometric Fourier series के coefficient है, and ck is the coefficient, or ck conjugate is the coefficient of कॉम्प्लेक्स फोरियर सीरीज। ठीक है, सी के कॉन्जुगेट बेसिकली सी के का ही आपने लेना है, कॉन्जुगेट लेना है। तो अगर हम इसको सेपरेटली मेंशन करें, ए के बी के फॉर्म में ना लिखें, तो सी नॉट इज इक्वल टू ए नॉट ओवर 2, which is 1 over 2. The substitute, this is my a naught. Okay, तो 2 2 से कैंसिल हो गया, so this is my a naught. और अगर c के लिखूं, c के is equal to this one 1 over 2. Substitute the value of a के and bk. So you can take f of x common from this. So I am left with this term in the end, and this by using the Euler's identity, it is equal to e to the power minus iota k omega x. This minus come because of this minus. So my ck is equal to this one. So you only, if you have to find the complex Fourier series of any function, you only have to calculate this coefficient ck, which is equal to 1 over t on the whole period x naught plus t f of x e power minus k omega x dx. This दूसरा वाला ना भी करें, सी नॉट ना भी कैलकुलेट करें, तो वो आप किसी से ही निकाल सकते हैं। ये अगर सेपरेटली करना है तो वो भी किया जा सकता है। Okay, let's solve this example one. The lengthy one example. I have evaluated all the terms, not over here, but I will evaluate it over here. So find the complex form of the Fourier series expansion of the periodic function this f of t is equal to cos of t over 2 from minus pi to pi. So this is from minus pi to pi. So the length of this interval is 2 pi. This t is equal to 2 pi. So omega is equal to 2 pi over t, which is 1 over here. So c naught is equal to 1 over t. from minus pi to pi cos of t over 2 dt. When t is equal to 2 pi, so 1 over 2 pi. The integral of cos of t over 2 is sine of t over 2 divided by this derivative of t over 2, which is 1 over 2. That is, I have to divide it by 1 over 2. Dividing by 1 over 2 means I have to multiply it with 2. Interval is from minus pi to pi, 1 over 2 pi. So sine of pi over 2, we'll take this 2 common, minus sine of minus pi by 2, cancel. So this is 1, this is minus into minus 1, which is plus 1. So 1 plus 1 is equal to 2 and pi. So C naught is equal to 2 over pi. Now let's calculate Ck, the only coefficient of the complex Fourier series. Ck is equal to 1 over t from minus pi to pi. F of t, e iota k omega t dt. This is your the value. Minus है इसके साथ. Minus. Here omega is equal to 1. So 1 over 2 pi from minus pi to pi cos of t over 2 e की power minus iota k t dt. Okay, ये आ गया. Here I will take this equal to I. तो अगर मैं I के क्योंकि ये दोबारा से repeat होगा, I is equal to that is 1 over 2 pi I, where I is equal to from minus pi to pi cos of t over 2 t to the power minus iota kt dt. So here I have to integrate it by integration by parts. So I can take cos t over 2 as first function, or this cos of t over 2 as the second function. Doesn't matter. Cos of, so if I take it as first function, so first function as it is, integral of second function, which is minus iota kt. So when I'm taking the integral, I have to divide it with its this coefficient minus iota kt minus iota k, limits of integration from minus pi to pi minus for the formula. So derivative of cos of t over 2, which is minus sine of t over 2. So I'm taking the derivative of sine of t over 2. So I have to multiply it with the derivative of the angle, which is 1 over 2. I have to multiply it. In this case, I have to multiply it. And into integral of the second function, which is minus iota kt over minus iota k minus pi to pi dt. Okay. So when I put cos of this limits of integration, cos of pi by 2, which is 0, and when I put cos of minus pi by 2, which is again 0, so this is actually 0. So both of these. Now minus into this minus into this minus. So I will get minus 1 over 2 iota k minus minus this minus. तो 2 भी कॉमन आ गया और आपके पास रह गया साइन ऑफ टी ओवर 2 into e to the power minus iota kt. Again, I will apply the integration by parts. So taking the sine t over 2 as first function as it is, integral of the second function minus iota kt over minus iota k, limits of integration minus pi to pi, derivative of the first function sine of t over 2, which is cos t over 2 multiplied by its derivative, and then integral of the second function minus iota k dt into this one. Acha. Now I will multiply both sides with this minus into this minus plus iota into this iota square minus 1. So again I have a minus sign over here. And k multiplied by this k is there. So this coefficient of this expression is minus 1 over 2k square. Sine of, for the limits, pi over 2 e the power minus iota k pi plus 1 over 2k square sine of minus pi by 2 e to the power minus iota k minus pi in this. And now this term minus and minus plus 2 minus and minus plus 2 into 2 4 2 into 2 4 k square. So minus and minus plus minus iota into iota is plus 1. So here I have plus this sign. 4k square 2 आ गया, and then I have integral of minus pi to pi cos of t over 2 e to the power minus iota kt, which is again this I. So I can write it I over here. And I can take this I on the left hand side, which becomes I plus 1 I minus 1 over 4k square I. So that is I have 1 minus 1 over 4k square I. अब now look at this minus 1 over 2 k square, ये माइनस यहाँ बाहर आ गया, then write this, and then you can take minus 1 over 2 k square common from this. Sine of pi by 2 is 0, and e minus iota k pi by using Euler's identity, it is equal to cos of minus k pi plus iota sine of minus k pi. This is 0, and this one is cos of k pi, which is equal to minus 1 to the power k. And again, this is equal to e to the power iota k pi. Yes, k ही पता चलता है. So sine of pi by 2 is 1. So this is minus 1 to the power k. And sine of pi by 2 is 1, e to the power iota k pi, which is again this k. So I have 2 times this, minus 2 times this, 2k square. This 2 is cancelled with this one. Or I have minus into minus 1. So this minus 1 multiplied by this. So 1 is added to the exponent of this minus 1 to the power k plus 1. और यहाँ से अगर मैं देखूँ तो I can take LCM 4k square minus 1 over 4k square I is equal to नीचे k square पे आ रहा है minus 1 the power k plus 1 over k square. So this k square is cancelled with this one. I को उस तरफ रखें, बाकी यहाँ ले आए. So 4 into minus 1 k plus 1 divided by 4k square minus 1. So this is my I. और ck मेरा फिर किसके इक्वल हो गया? ck is equal to 1 over 2 pi iota. So 1 over 2 pi, this I, not iota, 4 times, सिर्फ 1 over 2 pi साथ आ रहा है, 4k square minus 1. तो ये बन गया 2 into minus 1 k plus 1 4k square minus 1. So this is my ck. And what is my Fourier series? Fourier series of f of t is equal to summation ck e power iota k t. K is from minus infinity to infinity. Tk is 2 times -1 this, और इसमें एक साथ में ये पाई भी आ रहा है. This is 4k square -1 pi e to power iota k t. So this is my Fourier series. अगर मैं इसमें से ये है मेरा ck, which can be negative, which can be positive. और अगर मैं इसमें से k को 0 पुट करूं तो मेरे पास क्या आ जाएगा. यहाँ से अगर मैं देखूं ck c नॉट 0 पुट करूं k को 0 तो ये बन जाएगा -2 over -1 into pi k 0 which is 2 over pi. तो वो 2 over pi वही आ गया जो मैंने यहाँ कैलकुलेट किया था c नॉट. So if you have calculated ck, no need to calculate c naught separately. So this is your complex form of the Fourier series. And complex form of the Fourier series में से अगर आपसे कहा जाए कि ट्रिग्नोमेट्रिक फॉर्म कैलकुलेट करें तो ck is equal to 2 -1 k plus 1 4k square -1 pi, which is entirely a real number. So it means ck conjugate, it is equal to its conjugate, this one. So in that case, a naught, ये रिलेशनशिप हम यूज करेंगे फिर. A naught is equal to 2c naught because I have taken c naught equal to this. C naught equal to a naught over 2. So a naught is equal to 2 times c naught. So 2 times 2 over 5, which is 4 over 5. And what is ak? If ck is purely real, then ak is equal to, ak basically इसके equal है 2 times ck और bk फिर 0 हो जाएगा.
मैम एक सेकंड के लिए सवाल दिखा देंगे प्लीज.
This is your question.
सही हो गया मैम, थैंक यू.
Okay, then AK is actually जो मर्जी आप ले लें, आप ये वाला ले लें. AK is equal to this one. ये है AK और BK आपके पास, चूंकि ये दोनों इक्वल है तो BK इस केस में 0 हो जाएगा. अगर वो रियल है तो 0 हो जाएगा और अगर प्योरली इमेजिनरी हुआ तो ये AK यहाँ से 0 हो जाएगा. तो AK is 2 times CK. So this is 4 -1 K plus 1 over 4K square -1 this pi. ये एक आ गया. And then you can write the Fourier series, trigonometric Fourier series expansion of this function, which is, this is 4 over 5, so a naught over 2, so again 2 over 5 plus summation, and bk is equal to 0 in this case. So this is 4 -1 k plus 1, 4k square -1 pi cos of k omega x. Omega is 1, so cos of kx, and k is from 1 to infinity. ये जो पार्ट में कर रहे हैं ना, ये इतना सा, ये this is not the part of the question. We have done this question. ये आपका, you have calculated, expanded this into complex Fourier series. तो इतना ही है. ये अब मैं बता रही हूँ आपको कि अगर कॉम्प्लेक्स फोरियर सीरीज के बाद कहा जाए कि ट्रिग्नोमेट्रिक फोरियर सीरीज भी फाइंड करें तो इन्हीं कोफिशिएंट को यूज करते हुए यू कैन फाइंड a नॉट, a के एंड b के, विच आर द कोफिशिएंट्स ऑफ द ट्रिग्नोमेट्रिक फोरियर सीरीज, और वो आप सब्स्टिट्यूट करके इसी से डायरेक्टली कैलकुलेट कर सकते हैं ट्रिग्नोमेट्रिक फोरियर सीरीज. तो उसके लिए आपको इंटीग्रेशन करने की, अलग से a के b के फाइंड करने की जरूरत नहीं, जस्ट ये यूज इस रिलेशनशिप. ठीक है, तो ये दिस इज नॉट द पार्ट ऑफ द क्वेश्चन. ये मैंने आपको बताया है कि जब आपके पास कॉम्प्लेक्स फोरियर सीरीज गिवन होगी, जैसे कि कॉम्प्लेक्स फोरियर सीरीज जो हमने ऑलरेडी फाउंड कर ली फाइंड कर ली, उससे आप ट्रिग्नोमेट्रिक फोरियर सीरीज एक आसान तरीके से भी निकाल सकते हैं कि अगर आपको इफ यू नो द रिलेशनशिप बिटवीन द कोफिशिएंट्स ऑफ कॉम्प्लेक्स फोरियर सीरीज एंड ट्रिग्नोमेट्रिक फोरियर सीरीज, तो उससे आप यहाँ से इजीली कैलकुलेट कर सकते हैं। ठीक है, और अगर आपने कैलकुलेट की हो सीरीज, ये सीरीज कैलकुलेट की हो, यानी कि ट्रिग्नोमेट्रिक फोरियर सीरीज कैलकुलेट की हो, तो उससे आप ये वाली निकाल सकते हैं बाय यूजिंग दिस रिलेशनशिप कि ये है आपके पास ए नॉट और ये आपके पास फोरियर कोसाइन सीरीज है। तो ये है आपके पास ए के, तो उसी से आप दूसरी फोरियर सीरीज निकाल सकते हैं। ओके, तो डन दिस क्वेश्चन। इसमें ये पार्ट हुआ है, लेकिन ये सारा थोड़ा सा कॉज ऑफ टी ओवर टू को आप यू ये अप्रोच भी यूज कर सकते हैं। जैसे मैंने तो इंटीग्रेशन बाय पार्ट्स किया है और evaluate कर लिया है, you can use this technique as well. Because of t over 2 you can write it equal to this one and then combine the coefficients of this exponential function and then integrate it. और फिर इंटीग्रेशन के बाद यहाँ से जाने में get involve the lot of other calculations, इसमें ये कैसे आएगा ये आपने निकालना होगा। ये टेक्निक यूज कर लें या इंटीग्रेशन बाय पार्ट्स कर लेंगे, दोनों में से जो बेहतर लगता है वो थोड़ा सा, मुझे ज्यादा लेंथी लग रहा था इस तरह से, तो दोनों में से कुछ भी यूज कर लें। ठीक, तो बस ये आपने कैलकुलेट कर लिया। और ये अगर कैलकुलेट करना है तो इसकी वजह से मेरे ख्याल में ज़रूरत नहीं है, लेकिन बात वही है, कॉम्प्लेक्स फोरियर सीरीज और ट्रिग्नोमेट्रिक फोरियर सीरीज अगर कैलकुलेट करनी है तो उसी से ही आपने बात एक्स लिखा ये यहाँ किया जाता है। So I will upload these lectures on LMS and as well as the recordings of the lecture. So you are given the question example 2 as a practice question. Do this practice. And so far we have done uh, trigonometric Fourier series, how to calculate trigonometric Fourier series, and if the function is even, then it consists of the cosine terms only, dk is equal to 0, and if the function is an odd function, then the a naught and ak are all 0, no need to calculate them. You have only you only need to find bk, and the Fourier series for an odd function consists of sine terms only. And then you learnt about the half uh, series expansion and the full series expansion of some non-periodic function, um, which is again we find the trigonometric Fourier series for those periodic extensions. And then the last you learned about the complex form of the Fourier series or the complex Fourier series, which is derived from the trigonometric Fourier series, and the complex Fourier series is actually the exponential form of the Fourier series or exponential series or exponential form, right? And do these practice questions. Question. So I will stop here. Any question?